So our group studied the various lifestyle factors that influence cognitive performance. We have Dave, Francis, Akil, and Amelia. So clearly, cognitive performance is a critical aspect of the quality of life, can affect the ability to think, learn, remember, and make decisions. Past studies have aimed to assess the factors that influence cognitive score, but there is still a lot to be studied. The dataset that we chose was from an online resource and gives a comprehensive analysis of human cognitive performance based on lifestyle factors and demographic attributes. We all chose exploratory observational studies. They are observational because we're not manipulating any variables. The data is simply recorded without intervention, and they are exploratory because the studies aim to investigate patterns, trends, or relationships without a strong pre-specified hypothesis. Our dependent variable is cognitive score, and our independent variables, we have a large range of independent variables. Some are continuous and some are categorical, but there are a lot of interesting interactions to look at here. For a general methodology, we diagnose and improve the full MLR model. We diagnose it using different tests to test the assumptions of linear regression. And then we improve the full model based on those assumption checks. These can be things like centering or transformations. And then we use advanced diagnostics and remedies. We validate the model using k-fold cross-validation, and then, of course, additional hypothesis testing and conclusions. So my name is Francis, and my research question was, do age and caffeine intake interact with biological sex at birth to impact cognitive score? If so, what is this interaction? For my initial model and hypothesis, Y cognitive score was my response variable, and my predictor variables were age, biological sex, and caffeine intake. X1, X2, and X8, X2 were my interaction effects. My full MLR model is here, and my null hypothesis states that neither age nor caffeine intake interact with biological sex at birth to impact cognitive score. And my alternative hypothesis was age and/or caffeine intake do interact with biological sex at birth to impact cognitive score. I ran an initial ANOVA test and a full model GLT test. Here shows analysis of variance table between model 1 without interaction effects and model 2 with interaction effects. The p-value was quite large, 0.2985. So this shows that the interactions between age and gender and caffeine intake and gender are not statistically significant. So for my assumption checking, I check things like linearity, homoscedasticity, normality of residuals, multi-collinearity, and outliers and influential points. I did this by looking at a variety of different test results and plots. The one that stood out was normality of residuals. Clearly, looking at the QQ plot right here, the residuals are not normally distributed. They don't fall directly on this diagonal line. And an Anderson-Darling test was run and showed a p-value that was very small, confirming that the residuals are not normal. There was also a multi-collinearity issue as the VIF values were quite large around gender and the interaction terms. So to improve our full model, I used centering for the multi-collinearity issues. This was good because all VIF values dropped below 5. And then I also tried transformations for non-normal residuals, like the log transformation shown here, which clearly did not help the non-normality issue. The square root transformation, which helped a little bit, but brought about a new issue in heteroscedasticity, which was confirmed with a new BP test. And then I tried a Box-Cox transformation. However, there was no issue of non-constant variance, and the optimal lambda value was shown to be about 1, so this was clearly not right. The ending model was a center model without transformations. So next was advanced diagnostics and remedies. I used bootstrapping for robustness. Since we have a non-normality issue present, this allows for the estimation of confidence intervals without assuming normality of residuals and accounts for influential points. It allows for the judgment of the stability and reliability of conclusions, and also minor assumption violations now have minimal effect. I validated the model using k-fold cross-validation. The average RMSE for the center model across 10 folds was 22.884. So on average, the model's prediction was plus or minus 23 points off from the true cognitive score. Because the cognitive score ranges only from 1 to 100, this error is considered very large, or about 23% of the entire scale. Based on my research question, dropping predictors was not an option, so bootstrapping for robustness for hypothesis testing was the route that I chose. So for final hypothesis testing and conclusions, bootstrapped confidence intervals were used to estimate confidence intervals without assuming normality. The confidence intervals are shown here. Age and gender and caffeine gender both contain 0 in their confidence intervals. Therefore, we fail to reject the null hypothesis once again. We're just confirming it more robustly. And then a ANOVA test was also conducted to compare the full center model against a reduced center model. And the results are shown here. P-value is quite large again, so we can say that there's no evidence that the interaction terms contribute meaningfully to the prediction of cognitive scores.
Our next hypothesis investigates whether daily screen time has the same effect on cognitive scores across different exercise frequency levels when adjusting for reaction time. We wanted to determine if exercise could buffer the negative effects of screen time. This inquiry and its observational nature informed the full model development. Our multiple linear regression model predicts cognitive score using daily screen time, reaction time, and exercise frequency coded as dummy variables for medium and high groups. Interaction terms between exercise frequency and screen time were also included. We hypothesized that exercise would moderate the impact of screen time. While individual predictors were statistically significant, the general linear test comparing the full and reduced models showed a p-value of 0.0617, suggesting no significant difference once interaction terms were added. We validated our model by checking assumptions. Linearity was supported with only minor curvature at the extreme fitted values. Brown-Forsyth tests show homoscedasticity overall, although minor fanning did appear. The Anderson-Darling test suggested slight non-normality, but with 80,000 observations, the central limit theorem justifies normal-based inference. Multicollinearity was not a concern, with all VIFs below 2, while influence diagnostics showed no undue outliers or leverage points. We made improvements to address assumption violations. First, we centered our continuous predictors, reducing multicollinearity, particularly for the interaction terms. Although we attempted a square root transformation, it offered negligible improvements to normality while increasing heteroscedasticity. Therefore, we adopted a center model without transformation. Minor assumption violations at the tails were accepted and addressed through bootstrapping, leveraging the large sample size. Advanced diagnostics confirmed the model's stability. Cook's distance and DF beta showed no overly influential observations. Bootstrapping with 1,000 resamples provided robust confidence intervals for all coefficients, further validating that minor assumption violations had little practical effect. With the large sample size and robust methods, we could trust reliability of our model. To evaluate predictive performance, we used 10-fold cross-validation. Both the full and reduced models had virtually identical results. RMSE about 11.03, R squared of about 0.771, and MAE about 9.02. Removing interaction terms made the model simpler without sacrificing generalizability, supporting the selection of a reduced model. Finally, hypothesis testing showed no strong moderation effect by exercise. The GLT p-value was above 0.05, and the bootstrapped 95% confidence intervals for reaction terms were narrow and included near zero effects. In conclusion, while exercise independently improves cognitive performance, it does not significantly buffer the negative impact of daily screen time. Our model's robustness and predictive strength further supports these findings.
Do diet and/or sleep duration interact with memory score to impact cognitive score? And if so, what is the interaction? To explore this, we built a full multiple linear regression model, and our predictors were sleep duration, diet type, and memory score, plus two key interaction terms, diet with memory score and sleep duration with memory score. We tested the hypothesis that neither interaction term would significantly impact cognitive score. The initial ANOVA test showed that the interaction terms were in fact not statistically significant, with a p-value of 0.3289. Next, we checked model assumptions. Linearity was met, but mild heterostaticity was observed with a Brush-Pagan test. Normality showed minor deviations at the tails, which is acceptable with large samples. Variance inflation factors suggested mild but acceptable multicollinearity, mainly around the sleep duration with memory score interaction. And finally, there were a few influential points which were accounted for through bootstrapping. To improve the model, we tried centering and transformation techniques. However, centering was not necessary, and box-cause transformation show an optimal lambda close to 1, suggested that no meaningful transformation was needed. Thus, we retained the original cognitive score without transformations and addressed mild assumption violations through bootstrapping. Further diagnostics confirmed that there were no overly influential points affecting our model. Bootstrapping with 1,000 resamples provided robust confidence intervals, validating that interaction effects were in fact not statistically significant. And this helped ensure that any minor assumption violations were properly addressed. Finally, we performed a 10-fold cross-validation, and the average RMSE was about 21.19, meaning that the model predictions were approximately plus minus 21 points of the true cognitive score. Given that cognitive scores range from 0 to 100, this represents about 21% prediction error, which is moderate but acceptable given the large sample and complexity of the question. Dropping predictors was not an option because of the nature of the research question, so bootstrapping was critical for robustness. Well, in conclusion, there was no statistically significant interaction between diet or sleep duration and memory score in predicting cognitive scores. Bootstrapped confidence intervals confirmed that the interactions effect were in fact small and not meaningful. And ultimately, while diet and sleep may have independent benefits, they do not significantly interact with memory to influence cognitive performance in this model.
My research question for this project was, do reaction time and caffeine intake interact with diet type to impact cognitive score, and how does the human model compare to AI predictions? The variables that I explored in this study were caffeine intake, denoted X8, and reaction time, denoted X9, both of which are continuous variables. I also considered diet type, labeled X5, which was treated as a categorical variable with 3 categories: non-vegetarian, vegetarian, and vegan. I also had y hat AI, which represents the AI predicted cognitive score as an additional continuous outcome used for comparison later in the analysis. The primary research question was formalized through the following hypotheses. Under the null hypothesis, H0, none of the predictors, reaction time, caffeine intake, diet type, or their interactions have a statistically significant effect on cognitive score, meaning those betas are all equal to 0. Under the alternative hypothesis, HA, at least one of the predictors significantly impacts cognitive scores, meaning at least one of those betas is non-zero. I specified a full MLR model, including main effects and two-way interaction terms, as you can see on the slide. The reduced model was just an intercept-only model, assuming cognitive scores vary randomly around a mean without any influence from the predictors. Before drawing any conclusions from the model, I conducted a thorough diagnostics. First, heteroscedasticity was detected. The residuals versus fitted plot revealed a funnel shape, which was statistically confirmed by the Brown-Forsyth test, or BP test, with a p-value less than 2.2 times 10 to the power minus 16. To address this, I applied robust standard errors using HC0 estimator, which corrected inference validity. Second, a normality deviation was observed. As you can see, the QQ plot showed mild deviations near the tails, and the Shapiro-Wilk test rejected normality with a very low p-value score of 7.07 times 10 to the power minus 8. However, because of the large sample size of approximately 80,000, I relied on the central limit theorem and proceeded without transformations. Third, multicollinearity was assessed. Generalized VIFs showed that most predictors were below 4, with diet type and some interactions slightly elevated but still within the acceptable range. Thus, no predictors needed to be removed. After applying robust standard errors, the residual spread became substantially more uniform, further mitigating heteroscedasticity concerns. Overall, after these adjustments, the model satisfied regression assumptions sufficiently for valid and reliable interpretation of the effects of the predictors. To further validate my model, I performed bootstrapping and K4 cross validation with K equal to 10. Bootstrapping with 1,000 resamples confirmed the stability of my coefficient estimates. In particular, it reinforced the strong negative association between reaction time and cognitive performance with minimal observed bias. In addition, a tenfold cross-validation yielded a cross-validation R-square of 0.6839 with reasonable prediction errors, an RMSE of 12.97, and a MAE of 10.56. Together, these results validate both the internal robustness and the external predictive ability of my MLR model. Finally, I compared the human-built model's cognitive score to the AI-generated predictions. The AI model achieved exceptionally high predictive accuracy with an R-square of 0.9848, indicating almost perfect alignment with the actual cognitive scores obtained from the human model. Furthermore, the regression slope of cognitive score on AI predicted score was approximately 0.987, suggesting that the AI predictions closely match the scale and the variation of the true outcomes. While the human developed model offered valuable interpretability, the AI model outperformed it in an overall predictive precision across the dataset. To conclude, our project examined how lifestyle and demographic factors like reaction time, caffeine intake, diet, sleep, exercise frequency, etc., relate to cognitive performance. We found that these individual factors strongly influence cognitive scores, but interaction effects between them were usually not statistically or practically significant. Using bootstrapping and cross-validation, we confirmed the stability and generalizability of our models. Minor assumption violations were effectively addressed through robust statistical techniques. Additionally, AI models achieved very high predictive accuracy, showing the power of combining traditional statistical methods with machine learning. Overall, while individual healthy behaviors are clearly important for cognitive function, their interactions play a smaller role. Future research could explore more complex dynamics to better understand cognitive health. Thank you.